Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be the next of my Tactica Tutorialis science lesson videos. And today we're going to be doing a GCSE physics / triple science topic on gas pressure and Boyle's law, which are two exclusive triple science topics that also are very fundamental to parts of A-level physics and to the full kinetic theory of degree physics. So there's plenty here if you are interested in physics in terms of taking it forward for you to dive into. It also has a very strong historical context. Some of the research done around this theory is what led to, supposedly, the Industrial Revolution. It only worked because of this theory and understanding how it all came together. So, we've got plenty to get into today. This is essentially a full subtopic of about 3 or 4 lessons taught in one video. So I'm going to be going quite quickly and this video is going to be quite long. I will provide solutions videos to every exercise linked in the description as always, and you can check those out when you've attempted the exercises that I have for you. So what we're going to cover today is we're going to cover how pressure comes about in gases as a quick recap of the particle model. We're then going to establish the relationships between pressure and temperature in a gas and pressure and volume in a gas, also known as Boyle's law. We're then going to explore work done in terms of modifying pressure, which is where the Industrial Revolution part comes in. And then at the end, as a bonus for you A-level minded people or A-level students revising for something, we're going to have a look at how we can create the ideal gas equation. It will not be the full kinetic theory derivation of the ideal gas equation. That is an entire lesson in and of itself, pretty much on its own, that derivation. So I'm not going to do that, but I will show you in shorthand how what we do today links to and creates the ideal gas equation. So we've got plenty to get on with. Make sure you have your notes on hand. If you want to make sure you have your prior knowledge in check, you want to make sure you have an idea about the particle model and have work done as the two ideas in your head. Conveniently, I have a lesson on work done, and I think I've done the particle model in at least one video already. So, without further ado, we have plenty to do. Get your notes ready, and let's begin. Alright, so here is your starter activity for today's lesson. I know you've seen the particle model 100,000 times up to now, especially if you are a current sitting student, but it never hurts to have this fresh in your mind before we start off with this topic. So, you have 2 tasks to complete. The first revolves around this box. I'd like you to draw the box, and then in it, I would like you to draw the particle model for a gas. You don't need to draw hundreds and hundreds of particles, but make it clear what the particle model is like in a gas. When you've done that, there is a sentence for you to complete. Gas particles move something and something, often something, with each other and their container. So fill in those 3 blanks to describe the motion of gas particles. Once you've done that, in the description will be the solutions video for this. I'm not going to go through it in the main video to keep this moving. So when you're done, check the solutions in the description and then we will move on and talk about pressure. All right, let's have a talk about pressure in gases. Where does it come from and how do we calculate it? So the first thing to make clear is something that we talked about in the starter, and that is the idea of collision. So as we talked about in the starter, if the gas particles are moving around, as they do, they will bang into each other and bang into the container. So if I have some particles inside here, obviously there would be a lot more than this. There'd be billions and billions of particles in here, realistically. If I have a bunch of particles in here and they're all moving around very, very quickly and randomly, they're all going to bang into each other. And quite often, one of them will, for example, bang into this. One of them might travel in that direction and bang into the wall or the surface of the balloon. This one then might do that, and this one might do that. This one might be going off in that direction, but eventually it's going to hit that or bounce off and bounce somewhere else. This one might be going in that direction, but it's going to hit that wall. Eventually they will bang into and collide with the container. Now, when an object hits another object, if you call back to some of the other stuff you do in GCSE science and physics, you should be aware of what happens. If I, for example, were to push my pen against my hand, the pen tip is going to be my particle. It bangs into it, and that causes a force to act on my hand. Probably better example, if this is my wall, my rubber over here, and there's a particle bangs into it, a force acts causing it to move. We talked about Newton's laws in a previous Tutorialis video. And that means that there is, as I say, a force on the container, which I'm going to not call F here, but you generally would know it as capital F. And this force is obviously a vector, so it has a direction. And the way that force acts is outwards, at right angles. So for example, if this particle bangs into this wall, at right angles to the wall, that's going to be the force. If this particle comes along and bangs into this wall, then at right angles to that, that's going to be the force. I know it's slightly counterintuitive looking at the exact angle, but bear in mind balloons are often quite circular, so that would work for that. And all of these will happen. So you've got a force this way. That will be your force. This one, force acting out that way. That will be your force. And so on and so forth. You have outward acting forces. And that is what causes balloons to inflate. As the gas particles bang into the balloon, they push it outwards. They cause, via Newton's laws, a change in its state of motion. They cause it to accelerate and move. And because balloons are stretchy, they're able to expand as they are filled up with more gas particles banging into them. And when you stop putting air into them, the constant collisions sort of balance out and the balloon cannot expand anymore because the forces are all balanced, and generally it wants to constrict on itself. So its own will to contract, if you like, is balanced out by the outward forces, and it all reaches an equilibrium. So that is what happens with the particles. However, there is a further consideration when it comes to pressure. And the best ways I can model this is to think about those old bed of nails things that you used to find in old haunted houses and horror attractions and the like. So if you were to sit down and lie down and land on a nail, I don't have a nail to hand, but if you were to lie down and land on one nail, it would hurt like nobody's business. It would really hurt. Whereas if you were laid out on a bed of nails and you laid across it, you don't get hurt. It's possibly not the most comfortable experience in the world. I've never done it myself, but you don't get hurt. However, the force on those nails is exactly the same. You have a certain weight and you're putting all that force onto the nail or nails, but because when you've got the bed of nails, the force is more spread out, and that is due to the area of the surface. So this section is to do with a lot more of general forces and motion and mechanics, but it's very much applied here. So if I had a force of 30 newtons acting on the tip of here, that would be quite a lot, and it would hurt quite a lot. Whereas if I had 30 newtons acting all across here, that force is spread out a bit, so it's the same size, but it feels smaller. And what that is called, that sort of spreading out of forces and the difference between forces and area, is the pressure. And I will define this mathematically in a moment, as well as the force. So those are some slightly long form notes. If you don't want to copy it all down, I don't blame you. But if you wanted to know it all, I would say that this bit is probably the more important bit in terms of explaining what's going on. That is the important bit. The collision of particles causes a force on the container, and because that surface being hit has an area, that affects the pressure as well as the force. So let's do this mathematically, and then I will give you a worked example that I'll provide the solutions to in the description. So let's talk about the equations and put that definition of pressure into something we can actually use. So as we've talked about, pressure is based on the force that is acting and on the area of the surface being acted on. There are two variables in there, which is why I've got my formula triangle pre-drawn like this. So how do you think that equation will look? Based on what I've said, particularly think about our bed of nails example, how is that going to look as an equation? If pressure force and area were related, what would it look like? Give yourself 30 seconds and think about it, pause the video, and then we'll go through it. So hopefully you've done that. Pressure is defined mathematically as the force, with a C, not an E, force divided by the area. Or, in symbol form, P. Now, I write it with a capital P. You may see it, depending on your specification, with a lowercase p. I've always seen it as capital, and I will continue to keep it as capital so it doesn't look like density. Capital P is F over A. And that is the symbol equation and the word equation for pressure. Those you're absolutely taking down. Now, if I was filling out my formula triangle, I can see that pressure is force divided by area. So area has to be on the bottom and force has to be on the top. And pressure, therefore, is also on the bottom. You can therefore use this to help you rearrange the equation if you so desired. Now, we have one more thing to talk about here, and that's the units of pressure, force, and area. So, force has a unit of newtons. We saw that in our Newton's laws video, and, well, they're named after Isaac Bloomin' Newton. Yes, they're in newtons. Now, area is measured typically in meters squared. You may remember from, for example, our video on work done, that distance is measured usually in meters. All length things are generally put into meters when we work them out. And since an area, you may remember from maths, is two lengths multiplied together. For example, the area of this square would be, the rectangle is that length times that length. That would be the area. Therefore, it is meters multiplied by meters, which is meters squared. Pressure, you can therefore intuit the unit based on the calculations and what you've already been given. If pressure is force divided by area, force is measured in newtons and area is measured in meters squared. So I'm dividing by meters squared. So the unit of pressure is newtons per meter squared. Now, sometimes, and this is probably going to vary on your school as well as whether you're at GCSE or A level, you will also see it given in what we call Pascal. So Pascal is the other unit of pressure. They mean exactly the same thing, newtons per meter squared, but rather than write this down all the time, it was quite common to write it in Pascal. Your school may teach it either way. Personally, I'm a big fan of Pascal, but some of you may have it in newtons per meter squared. Both are correct. They are interchangeable with one another. So on the screen in a moment is going to be two calculation questions involving this stuff. I would like you to have a go at them both, and then when you're happy, go to the link in the description to Calculation Solutions 1 so that you can have a go at answering that question. When you're happy, we'll move on and talk about the relationship between pressure and temperature. All right, we're now ready to talk about gases in particular and start looking at the gas laws. So this is going to be the first relationship we're going to establish today, and that's between pressure and temperature. So first off, a quick recap from something you may have met before and you'll certainly meet when you look at temperature and energy. So temperature is actually quite closely tied to energy, but not necessarily to heat energy. There is a difference. What actually happens with temperature is it is a measure of the average kinetic energy of the gas particles. I know that might sound a little bit weird, but what that means is if the temperature is higher, that means that the particles in the gas are moving faster. That is what that means. If you give them more heat energy, yes, their temperature will increase. But if you think back or you know about specific heat capacity, you know that the amount of heat energy you give is not strictly the same as the change in temperature because of E equals mc delta T or mc delta theta, or however you've met it in the past. So what temperature actually measures is the average kinetic energy, not the kinetic energy of that one particle, but the average across all of them. Now, what that therefore means is if we turn up the heat and increase the temperature in our gas and we make it hotter, for example, we have some gas sealed up in a test tube and we put it over the top of a Bunsen flame. If that happens, the kinetic energy on average will go up. And that means by E equals a half mv squared, the particles will move faster. Now, if the particles move faster, they have a greater speed and a greater velocity. And that increases their momentum, which means that when they bang into the walls, there is a greater change in momentum, which is something we did in a recent video. And what that does is increases the force. This pen, come on. So if you think about that in terms of collisions, if you're moving quite slowly and you hit a wall, there's not much force on anything. Or if you say just tap your hand together quite slowly, doesn't feel much. You don't feel much force. You do it at high speed, you really feel it. You can feel the force a bit more, not the force with a capital F, by the way. You feel that impact force a lot more if you are doing it at high velocity, so there is more force if the particles are moving faster. And if we go back to our original derivation of pressure, we know that pressure is related to force by P equals F over A. So if F goes up, P must also go up. So if you think about it in total, what happens when you turn up the heat on a gas? The particles start moving faster as their temperature goes up. Their average kinetic energy increases. This means they move faster, hit the wall with more speed, thus increasing the force on the wall, and thus the pressure goes up as well. And that leads to a relationship, we say, between pressure and temperature shown on this graph. Now, there's a caveat that I'm going to put in a moment, and we'll draw this graph last of all. That's going to be your task for this section. So, we say that pressure P and temperature T are two words: directly proportional. Asterisk. And I'll come to that asterisk in a moment. So what that means is that pressure and temperature are related by a straight line graph through the origin. Now bear in mind, the origin of a temperature graph is at 0 degrees Kelvin, absolute zero, which is minus 200 degrees. So if this temperature was in, shall we say, degrees C, and that was 0, that's actually not absolute zero. So a typical PT graph will not actually start at 0. So I will give you an arbitrary point there for you to draw the rest of your graph from. So you're going to have to complete a direct proportional curve starting there as to what you think that looks like. But there is one asterisk that I want to address before you do the task. You can do this now, but this is something I need to get in your notes. So this relationship works if and only if the volume is constant. So what that means is if you have a fixed volume, for example, this box has a fixed volume. You can't change it. If I turned up the heat under here, the gas that's in here would have its pressure increased directly proportionally to the temperature. However, if I had, say, a balloon and I inflated it and then heated it up some more, then that volume can change because the balloon might expand or shrink, and that means that this relationship breaks. You have to have constant volume for this relationship to work. So 30 seconds to a minute, have a think, maybe look back through some notes you might have from maths about direct proportionality, have a go at drawing that graph. And what you should get is something that looks a little bit like this. Now, yours will look better than mine. You have a ruler. So what you will have is a straight line graph that is increasing as t goes up, p goes up, because we talked about that here. And it is a straight line, and in this case does not cut the origin of 0 degrees Celsius. It would cut the graph. In fact, I'll do this just in another color. If I was to track that back, that would be t equals absolute 0. That is when it's where the origin is, if you wanted to track it back. But that's just a little aside. So those are your notes on pressure and temperature. Average kinetic energy, thus increasing speed, force, pressure, directly proportional if volume is constant. And please do draw that graph correctly if you had a go at it and got it wrong. Right, now we get to do Boyle's law. So now that we've had a look at pressure and temperature, we're going to get into pressure and volumes relationship now, and what is known as Boyle's law. So if the volume of a container, so let's come back to our box. So if I've got a box and it's full of gas particles, if I then was able to squeeze this box down so it was only that big, then all those particles that were this spread out are now packed into half the space. So the volume has now decreased from all the box to half the box, for example. Or you could think of it, for example, as having a sort of half stiff balloon and sort of squeezing it down a little bit, or anything like that, or just pressing down on a syringe is probably the best example I can give you. If that happens, then what's going to happen to the collisions between the gas particles and the container? Well, there's going to be more of them, because the particles are now packed together in a smaller space. So to use a sporting analogy, imagine playing a game of football where you had 11 aside on half a pitch. Or maybe you had, for example, I don't know, Formula One, where all the cars could only use the left-hand half of the track. You are packed into a smaller space, and that means that there's going to be more collisions between you. They're going to be banging into each other and banging off the walls a lot more. However, they're not moving any faster. So the force of a single collision is the same, but the overall force will increase. This is because more collisions at same individual force. So each particle might have a force of 5 newtons when it hits the container wall. That's way too big, but go with it. Say 5 newtons, and that's not going to change. But instead of there being 20 collisions, there's now 40 collisions. So the overall force, instead of being 20 times 5, is now 40 times 5. So the overall force has increased. And that, as we've seen a couple of times already, causes the pressure to increase, because remember, P equals F over A, as we talked about earlier in the video. So what we've established is that as volume decreases, pressure increases, which is the opposite relationship to what we had with pressure and temperature. They went up together. In this case, as V goes up, P goes down, and as V goes down, P goes up, if you follow. And the relationship for that we describe that as is inversely proportional, which is a term you may have come across before. If you haven't, don't worry. So I'll address the asterisk in a moment. So that means that pressure P is proportional. That's a proportionality symbol for you less people who've not seen all of that in maths before. Proportional to 1 over volume. It's not P equals 1 over volume, but it is proportional to 1 over the volume. Now the asterisk is very similar to our previous asterisk, except we've just got to change a few words. So remember, the PT relationship of direct proportionality only held because of a constant temperature, a constant volume. You mess with the volume, the relationship breaks. Same's applied here. This inverse relationship only applies if the temperature is constant and there is an extra one, the mass of the gas. So what that's meant to mean is that if you keep the container at the same temperature and you don't change the amount of gas in it, then this relationship will hold. That's what the mass part is for. Because I could easily say, okay, I've now got half a box, but I've also taken away half the particles. So instead of having 100 particles in a full box, I've now got 50 particles in a half box. So I've changed the mass of my gas because each particle has a mass, and that means that this relationship will break. So you have to have a constant temperature and a constant mass, or, which is what you do with the ideal gas equation if you're an A-level person, a constant number of particles might be another way for you to remember it, though mass is probably what you'd be asked for on an exam. So that's the theory, get that down, and now we're going to show you the mathematics of Boyle's law. So this is what we established just now, is that pressure is inversely proportional to 1 over the volume. It is an inverse proportionality, so P is proportional to 1 over V, or it is inversely proportional to V, if the temperature, T, and the mass, M, of the gas are both constants. So, I'd like you to imagine a scenario for a moment. Imagine you have a box, and that box is a certain volume. We'll call it V1. And its pressure, you read it off with what we call a barometer, and its pressure you record as P1, whatever it happens to be. So take your box, then what I'd like you to do is squash that box down. I'd like you to make it smaller so that it is now at a new volume, and I'd like you to call that V2. And you'll read its pressure again with your barometer, and you'll find its new pressure, which is P2, for the pressure of the gas inside. Now, Boyle's law was established pre-industrial revolution. In fact, it was one of the first major steps toward a particle model, the particle model we see today, by one of the Irish scientists, Mr. Boyle. And he established a relationship between P1 and P2 and V1 and V2. And so, what Mr. Boyle found out, this was done experimentally, so I can't give you a theory, you'd have to see it practically, was this. P1 V1 was equal to P2 times V2. And this is now known today as Boyle's law. The pressure multiplied by the volume is a constant. In fact, the other way you see it written is this. Both of them mean roughly the same thing. So Boyle's law states that the pressure multiplied by the volume for a gas is a constant if this is true, constant T, constant mass, which means that if you change the volume of a gas, you can calculate the new pressure of the gas without having to do it experimentally. Or if you crank the pressure up on a gas, then the container, you can work out what size it will become. These two laws are very, very useful and are coming up in a lot of tests. I've seen them done, and you need to be able to use them both equally. Sometimes you will be asked to calculate this constant, which is pressure times volume. And sometimes you'll be asked, given some information, given 3 of these parameters, or this parameter and 1 of these 2, work out the 4th one. So the last thing to establish before I show you some calculations that you can practice is the units. Now, we already established earlier that P is in Pascal. And typically when you establish this constant, this will be in Pascal meters cubed rather than newtons per meters squared. I don't know why. I don't know why, in truth, it is. But it is usually written as Pascal meters cubed. You may see it as newtons per meter squared times meters cubed equals Newton meters, but we'll come on to why that might be an interesting unit in a moment. And because of this, the unit for volume is meters cubed. You're going to have to be very careful with volume to get it in the right unit, because remember, volume is length times width times height. It is 3 lengths multiplied together. One of them might be in meters, one of them might be in kilometers, and one of them might be in centimeters. Doesn't really matter. You've got to be able to convert all of them to meters, or whatever your question asks you, typically meters, and then get the volume in meters cubed. It might seem tedious, but you've got to get your units right in order to get this question correct. Technically, if you have the wrong units for these on both sides, it will still work. But for consistency, always put your units in meters cubed and always put your pressure into Pascal or newtons per meter squared, as you may remember. So that is Boyle's law. Coming up on the screen will be a couple of calculations as before. Solutions will be in the description linked as Calculation Solutions 2. Click that video, watch the solutions, and then come back and we'll talk about work done to wrap up the lesson. All right, so for the GCSE minded people in the room, this is going to be our last segment. Now I'm going to do one little bit at the end for the A-level crowd who might be interested in taking it further. And if you are GCSE, you are welcome to stick around for that. But this is the last bit of GCSE teaching that there is to do. So your last exercise is this top section here. Can you give me 2 ways to increase the pressure in a gas? When you've done that, I'd also like you to at least think, if not write down, probably for your own notes you should write it down, why? Why does that increase the pressure in the gas? So you can tell me what to do, and then how'd you do it? If you get finished and you're happy with that, give yourself a couple of minutes. When you're happy, you have a think about this one, this second question. Have a think about it. Off you go. Okay, hopefully you've had a chance to pause the video. If you haven't, do so now, because I'm going to give you the solutions based on what we've done today. So, the first way to increase the pressure in a gas is to increase the temperature. So we talked earlier on about the PT relationship, that direct proportionality, and that causes the pressure to increase when the temperature goes up. Why? More kinetic energy leading to more force per collision. So each particle, on average, is moving faster when you increase the temperature because you've cranked up their average kinetic energy, and that means they hit the wall harder, more force per each collision. The second way is the one we just talked about with Boyle's law, decrease the volume. And if you decrease the volume, what that does is it increases the number of collisions that you have. But bear in mind, this force per collision is actually unchanged because you haven't changed the temperature. If you have both of these going on, then both of these are true, and so the pressure ramps up even more, and that leads you to the ideal gas equation. But this last bit, this is something that I had actually not even considered before when I've taught this the first time. So, when you compress a gas, in a syringe, for example, I wish I had one on hand, but I don't. If you have a syringe and you compress the gas in it, you have to put some work in, literally. You have to apply work to the syringe to push it down. So doing work on the gas by compressing it causes an energy transfer. And the store that it is transferred to is called the internal energy store. Now, internal energy I'm not going to discuss here because it's sort of a side point that you do probably when you talk about energy overall. But by transferring to the internal energy store, this in particular explains this one. Because the internal energy is then used to, well, you can't keep a constant temperature most of the time. And generally that transfer to the internal energy store will end up in the kinetic energy store in the form of temperature. So that is the last point, and sometimes you get questions about why, in terms of energy, a gas will heat up, and generally you're talking about doing work and transferring to the internal energy store, thus increasing the kinetic energy. So, if you're purely GCSE minded and you don't really have an interest in taking physics further, then you are welcome to click off at this point. Thank you very much for your time, your hard work, and I hope you've enjoyed the lesson. Let me know any thoughts you have in the comments down below. However, if you are more A-level minded and you want to see how this fits into the ideal gas and kinetic theory of A-level and degree physics, stick around. We've got one more thing to do. Alright, just for fun, this is not a full Year 13 A-level derivation of the ideal gas equation. This is an extension of what we've done today to apply what we've done and show you a little bit about where the ideal gas equation comes from. So, first off, we need to remember the pressure-temperature relation. We just talked about it. We know that pressure is proportional to temperature. Now, this assumes, of course, constant volume, but when everything starts playing together, this will hold up to an extent. It is not a perfect relationship when you have changing volume, but there is still a relationship. Boyle's law says that PV is a constant. Therefore, P is proportional to 1 over V. That is what we established earlier, this particularly being Boyle's law, and this is what that means in context. So we can therefore say P is proportional to T over V. Because if pressure is proportional to temperature and proportional to 1 over volume, then if both of them are in play, then they're both affected like this. If I hold the temperature, the pressure will change as 1 over volume. If I hold the volume, the pressure will change proportionally to the temperature. So it stands to reason, and you do fuller derivations of this at A level, trust me, that pressure is proportional to both of them at the same time. It is proportional to temperature divided by volume. Now we also mentioned here that this required a constant mass of gas, which is another way of saying that is a constant amount of gas inside the container. And that also therefore means we could add a proportionality of, I don't know, M there. Or, as we typically do at A level, how we typically do it, instead of talking about the mass of the gas, because that's quite difficult to measure or difficult to categorize, we generally talk about it proportional to N, T over V, where N is the number of gas particles. I'm just going to move V across. So PV is proportional to NT. And all we therefore need is to work out what the constant of proportionality is. So we can change pressure, we can change volume, we can change the amount of gas particles, and we can change the temperature, and all of them work together in this intermingling ecosystem. And the constant of proportionality is this. PV equals NK, lowercase, T. Now, I personally prefer to write K as K subscript capital B. You don't have to. I personally prefer it to write KB rather than K, because that is Boltzmann's constant. It is a very important gas-based constant, and that right there is the ideal gas equation. Now, the derivation you do at A level revolves around momentum, changes in momentum, impact forces, and all sorts of stuff that goes on a very, very long time. This is very much shorthand based on what we've seen and making some assumptions. So we've assumed that it's proportional to T at constant V, so we can just roll V into that constant of proportionality. So when both of them are in play, T over V. This requires constant mass. So I've assumed it is proportional to mass linearly alongside temperature, but I've had to assume that because I can't actually mathematically prove it in this style of derivation. You'd have to do things with momenta and work it out forces in that way to actually prove that. And I know the constant of proportionality is KB because I've done this before. Again, I can't prove that to you right now. All I can do is show you that in theory, what we've done today allows us, through a little bit of sneakiness and a long derivation, to arrive at the ideal gas equation. This stuff matches up to this stuff, is what I sort of wanted to show you. Right, that is the end of today's lesson. That has been everything you need to know about gas pressure, gas laws, and a little bit extra about the ideal gas equation. I do hope you found today useful. There was a huge amount of information that I've thrown at you in this lesson. I've essentially covered an entire GCSE subtopic, about 2 to 3 weeks of teaching in one go, because I can't do anything practical with it, and I haven't got the right equipment to do that. So I've been able to condense the theory down with some calculus all in one lesson. This lesson would normally take you several weeks at school. So if you're a bit confused or you think I went a bit fast, that's okay. Work your way through the theory, have a go at the calculation examples that I gave you, and that should give you a solid understanding of most of it. And if you need to see it practically once you're back at school, then absolutely that is the best way to solidify seeing that this relation is true, that this relation is true. It is easier to do if you can see it and do it just as Boyle did for this one. It is really useful. Right, that is all for today. Thank you very much for your time, your attention, and all your hard work. Let me know what you think in the comments below, and if you have any suggestions for future lessons, I'm always interested to see what you have to say. Next time, I'm thinking we'll pop back to radioactivity. I did my lesson on properties of radiation quite recently, and I think I will have a lesson on nuclear decay just to tie those two together nice and easily. So, thank you very much for watching. This has been Tactica Imperialis, and this has been Tactica Tutorialis for gas laws and gas pressure at GCSE Triple Science. I'll see you all again. Bye for now.